Hello. All right. So now we have Yang Deng. He's recently submitted his PhD thesis and defended it, if I'm not mistaken, from Hong Kong Poly. And he also introduced us the project on automated data augmentation model. So please take it away, Yang.
Okay, hello everyone. This is Deng from Hong Kong Poly. Our work is AugPlug, an automated data augmentation model to enhance online building node forecasting. Okay, when machine learning models are deployed in the real world, the practitioners usually need to update the model. This process is called online model updating, online machine learning. Online machine learning is commonly used in the situation where the data is too large to be processed or the data distribution is constantly changed. It's commonly used in the many scenarios such as recommendation system and automatic driving. There are two key components in online machine learning. The first one is the model update strategy. It can be organized in these two dimensions. They are learning mode and the adaptation method. And the second one is the data used to update the model, which is also known as updating set in the machine learning community. For building node forecasting, which is a very typical task to benefit the downstream applications, such as for controlling the HVAC system, there are many research works based on online machine learning to improve the node forecasting accuracy. To our knowledge, almost all the works of online building node forecasting focus on data distribution changes and aims to keep the accuracy at a high level. Okay. We first look at the mentioned two components in the, for the online building node forecasting. First, for the update strategy, we observe that the majority of the published schemes falls into this table. We list some of them here. For example, for this SVM model, it designs a weekly routine update strategy and to update the SVM model during the COVID-19. The COVID period. On the other side, for the updating set, we observe that all these mentioned models prepare the updating set by using the latest arrived data. Here is a question. We consider that the collected data may not be effective in updating the model because the data could be continuously changed. So the model updated with using the history data could be one step delay to distribution change. As a result, the forecast accuracy could be still not good even after the model update. To figure out if this is a real question, we implemented one of the online building node forecasting models to check the effectiveness of the updating. The test building is a real office building with two year lengths. We trained an initial model using the first year data, and then we simulate the model deployment in the second year for 24-hour ahead forecasting. Here we compare the two types of forecasting accuracy. They are the model with its designed updating mechanism in their paper, and the initial model with the fixed parameters. The matrix is CVRMC, which is lower the better, and the dashed lines denotes where the update conducted. Then we have two observations from the curves of the forecasting error. First, the updates didn't always bring the accuracy improvement. Second, the model with updates even worse than that without updates, as shown in this highlight arrow. To figure out if this is a common phenomenon, we continue conducted a statistical analysis in this slide. We implement four schemes that designed with different update strategy. We tested these models on hundreds of public buildings, and we use A/B test to quantify the effectiveness of the specific update operations. For each update, we compare the results of with update and without update. Here we define an update as ineffective if the forecasting model doesn't achieve a better accuracy than that without update. Here the table shows that statistical results, and we also draw a histogram for better visualization. The results shows that there are about 1/3 of the update operations are ineffective, and 12% updates resulting in at least 10% accuracy decay. Okay, what's the solution? Generally, there are two directions to enhance the performance of machine learning model. One direction is to modify the model structure, such as the N layer loss function. That's quite challenging in this online scenario. Another choice is to generate data with similar characteristics as the future data, and then use such data to update the model. Intuitively, the second one is more promising in our scenario, but there are still some challenges. First, while most data generation approaches in building energy can enhance the data diversity to help the training model, they are not suitable for the data distribution change scenario. Second, directly forecast the dynamics of the building data is impractical, especially the interval between the two updates can be a very long period. Moreover, since there is no standardization to quantify the characteristics of the building data, preparing a suitable updating set requires manual effort. We leverage automated data augmentation, which is also known as AutoDA. It provides us a solution framework. AutoDA is a task of searching for data augmentation policy for a given dataset and has been applied in real products such as Google self-driving. The key aspects of developing AutoDA is the search algorithm to find the optimal policy. A typical search algorithm in AutoDA is reinforcement learning, where the RL agent explores the policies from the feedback of model accuracy. We follow this to design our solution. We first introduce the problem statement, and then we show the solution. In this scenario, the model deployed in a building can be denoted as a model sequence. The original updating set prepared by the online building node forecasting scheme itself is denoted as D-up, which is extracted from the observed data, and then the update strategy designed by the scheme is F-up. For each update, given the current model, the update function and the observation, then a policy tau is applied to transform the original updating set to a synthetic updating set that involves potential characteristics of the upcoming data. The goal of the data AutoDA is to find the optimal strategy. For the solution design, we follow the reinforcement learning, which is a commonly used framework for AutoDA. In this context, a controller ion, which is the RL agent, predicts a data augmentation policy from the search space. The forecasting models is updated to achieve an accuracy, which we denoted as R. R is the reward and will be used to update the ion controller. Next, we introduce the RL formulation in this data augmentation context, that is to define the state, action, and the reward. The state is the observed data stream during the model deployment. It consists of two parts in our paper. They are the data from the building systems and the records of the forecasting accuracy. For the action, the policy tau express a list of data transformation operations that were conducted sequentially on the original updating set. The operator is defined with three parameters: the type of transformation, the magnitude, and the probability of applying this operation. And we design a search space which contains several conventional time series transformation operations, such as scaling, jittering. Here we show an example of the data augmentation conduction in the right side, which consists of two transformation operations. The reward is the accuracy improvement, as shown in this equation. Then we introduce the RL agent design. Generally, RL agent in AutoDA is a RNN model, as we mentioned. We develop a LSTM model to predict a sequence of actions in an auto-regressive manner, where each action represents type, magnitude, or the probability. Moreover, there are two unique challenges in this context. The first one is the representation of the state. Generally, the neural network would design a fully connected layer to encode the input for extracting the information. In our scenario, the temporal dynamics of the observed data stream should be extracted because it can provide the insights into the characteristics in the future data. The second is the execution of the policy for different update strategies. In our context, there are 4 types of strategies which have different requirements for data size and diversity. For example, the fully retrained update strategy needs more diverse data than the fine-tuning method. We address this first challenge by designing a temporal convolution network, and we address the second challenge by proposing an adaptable data transformation module in the softmax function of the LSTM model. Okay, we put them together and use a PPO algorithm to train this reinforcement learning model. There are 2 concerns when applying the proposed data augmentation model for an existing online building node forecasting model. First is what features in building node forecasting needs to augment the data. The features can be categorized in these three types. In our work, the AutoDA model only conducted on the first 2 types, because almost all the load forecasting models only involves and we assume that the time feature could remain the same and don't need to do the data augmentation because almost all the load forecasting models only involve time features such as the hour and the day of the week. Second, how to integrate our model to an existing scheme. We use two examples to show that the practitioner need to insert a few lines of Python codes in their inference file. Then we present the evaluation part. The setting is same with the introduced statistical analysis in the motivation part, where the 4 different schemes are tested on hundreds of buildings. We compare the AutoDA model with 2 baselines that can also generate data or solve the data distribution change. Overall, after equipped with our proposed data augmentation model, the building node forecasting schemes improve the accuracy by 29% compared to the original schemes. In the right side, we also use a histogram to show the before and after. We observe that the ratio of the ineffective updates significantly reduced from the 31% to 17%. We use 2 examples to show the data augmentation policy can how to benefit the model update. This one is for a scheme with a univariant forecasting. The top figure shows the ground truth, and the bottom figure shows the comparison of the forecasting error. The dashed line are where the update conducted by the online load forecasting model itself, and the predictive policy is shown in the right side. We can see it can match the trend of the data change. And there is another example for multivariant forecasting. The input features are load and the outdoor temperature. Okay, we conclude this work as 2 points. We investigate the effectiveness of the online updates in the existing online building node forecasting schemes, and we show a significant proportion of updates have negative effects. We introduce the framework of AutoDA, based on which we develop a data augmentation model to search the suitable data augmentation policies. That's all of my presentation. Thank you for your time.
Thank you, Yan. Any questions from the crowd? Yes, I think the mic is coming.
Yes, thank you for your talk. I was wondering, does your framework also consider the problem of catastrophic forgetting, or is that something that additionally needs to be considered outside of AutoDA?
Okay, very good question. In our design, we haven't considered contrastive forgetting, which means the model learn the new knowledge while forget the previous knowledge. Because we consider the most important in our scenario is the model, if the model can behave good in current data. So if we update it correctly, it can perform have a high accuracy in current situation. So we don't think if it's we need to consider if it forgets the previous, because if we can predict what will happen in the future data, we can generate the synthetic data to that, and the model will be always perform good. So it can somehow solve the catastrophic forgetting. I think it's another dimension, I think.
Okay, thank you.
Any other question? We have some time at the back. Okay.
Test.
Yeah, I think it's really an interesting work, and I'm super attracted by the part you can actually visualize some policy that how we augment this data set. I was wondering, can you give us a bit more detailed example on how we kind of understand what kind of augmenting action like it really makes? I think it will be super beneficial for the building managers to analyze what might happening behind the drift of this building load distribution. Thanks.
Okay. Firstly, in our design, we have this slide. We have designed several time series transformations. These transformation operations are usually used in many time series related data augmentation, including the building energy. Yeah, the traditional data augmentation method. And we use these types, for example, scaling, jittering. Scaling means, you know that, for example, from the winter to summer, it's very hot, and the cooling load, many energy consumption, and the load can be larger than before. So it's maybe use scaling such as this kind of transformation to augment the data. Yeah, such like this. And our evaluation shows that if we check it by ourselves, and the augmentation transformation operator match the trend of this data distribution.
Thanks a lot.
I have one last question. Oh, there's one more? No. Okay. It was interesting to see that despite the augmentation, some buildings were still very hard, or they were still having not improvement even after augmenting data or when trying to do online forecasting. Did you guys look into those specific buildings? Was there anything interesting in why despite the online updates, it was still not improving?
Could you please repeat your question?
Around 30% of the buildings, there was still no improvement on, despite doing around that, right? 30% in the ineffectiveness, and there's still some percentage of them after AugPlug. Was there something unique about the scenarios, the buildings, where these or the?
Okay. It's a very question. This is a statistic that's 4 different existing online building load forecasting models. These models are published. Yes, there are. We implement their papers, their models, and we run them in hundreds of public building data. And overall, there are we statistically the update operation to see if they can improve the accuracy or didn't improve the accuracy, while compared and didn't do anything with the same And this 30% is overall statistic.
Understood. Okay. Thank you. Thanks, Yang. Once again, guys.